39. Our objective is to analyze graphs to determine end behavior, zeros, relative maximums, and minimums. So, polynomial function review. We have the basic f of x, okay, and this is our highest degree, okay, and then our next degree and so forth. And even if this was a 4 and this ends up being 2, we talked about how this is 0. We did static division. This would be 0 x cubed to make that space. It still exists, we just don't write it. Okay? This over here is just a review of our degrees. So we have no constant, no degree is 0, constant. Degree of 1 linear, and so forth, as we've been talking about for quite a while. So it says, where a sub n is not equal to 0, the exponents are all whole numbers, and the coefficients are all real numbers. As we talked about for a polynomial function, we cannot have variables as exponents. They have to be whole numbers. So the example here, a sub n is the lead coefficient. A sub o is the constant term. Notice there is no variable here. And n is the highest exponent, as I've already talked about. Now, new term here, even though we've been talking about it for a while, every time in the past we've talked about the domain and range, we talked about infinity and negative infinity. The end behavior of polynomials functions graph is the behavior of the graph as x approaches positive infinity and negative infinity. So as it goes left to right, the domain. Okay? Investigate the functions below to help us make a general assumption about end behaviors of odd and even degree polynomials. So you're going to use a graphing calculator to sketch these graphs. Okay? You can do this very simply. If you type in y equals x cubed, you would get now most numbers would be off your chart here, but we would get 1, 1, 0, 0, and negative 1, negative 1. But we also get negative 2, negative 8, and positive 2, positive 8. So we get a general shape, which we talked about before, that looks something like this. That is f of x equals x cubed. Now, if we went back in and put a negative in front of our x cubed and graph that, it would go the opposite direction. So in this case, we would have points negative 1, 1, 1, negative 1, and 0, 0 again, and 2, negative 8, and negative 2, positive 8. Basically a negative mirror image of our other function. And that's our f of x equals negative x cubed. Okay? Now to the fifth. Do the same thing, but taking it to the fifth. We're going to get a very similar shape. So we're starting at negative 1, 1, 0, 0, and 1, negative 1. I'll do it negative first this time. But this time 2, instead of being negative 8, is way down here at negative 32. And 2, instead of being at positive 8, is going to be way up here at positive 32. degrees. So what do you conclude based on this observation and what we talked about in the previous homework, 3.8, about the end behavior of the odd degrees? What's happening going towards infinity? What is happening? Well, the ends of the graph go in opposite direction. At the ends of the graph go in opposite direction. Okay? You can kind of guess maybe where we're going to go with even. This should all look very familiar to you. Our classic x squared. Negative 1, 1, negative 2, 4, negative 3, 9. 1, 1, 2, 4, 3, 9. Okay, 0, 0. There is our parent function parabola, x squared. What happens to negative x squared? It is the inverse going the opposite direction. Of x squared. X to the fourth is going to be very similar. It's just going to, once again, go a little bit faster. It's going to be a little skinnier. And it looks like a lot of nodes, but really it's not. Now, we've been dealing with quadratics for quite a while, and what was happening? What happened at the end behavior, the end where the arrows were going? Well, in this case, the ends of the graph go in the same direction. So what happened in the examples when the leading coefficient changed to negative 1? And this goes back to our transformation unit. Spell reflected over the x-axis. Okay? So now we're going to have a little bit of a chart here. So the end behavior is determined by the function's degree, whether it's even or odd, and the sign of this coefficient, leading coefficient, positive or negative. Okay, we're going to fill out this chart as a reference point for you. So this is going to be negative infinity and positive infinity. How you read this is as x approaches negative infinity, f of x approaches positive infinity. Okay? So here, this is going to be positive infinity, positive infinity. Here it's going to be negative infinity, negative infinity. And here we're going to have positive infinity, negative infinity. So once again, if you want to write this down here, this would read as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative f of x approaches negative infinity. Once again, if you want to pause and write those down, that's fine. But they're basically repeats in the same format. As x approaches positive infinity, f of x approaches negative infinity. So, look at what quadrants they're ending up in. Okay? Once again, this is quadrant 2, and quadrant 2 is negative, positive. And quadrant 1 is positive, positive. So all you do is fill in the blanks that way. As x approaches negative infinity, so it's going this way, negative infinity, this is going up. Y is going up towards positive infinity. So the non-math way says, as we go left towards infinity, we're going up towards positive infinity. And what's happening in quadrant 1? Well, as x is approaching, as it's going right, it's going up. So we're dealing with domain and range at the same time. We're looking at both. As we're going left, we're going up, and as we're going right, we're going up. Let's look at number 6. Well, we're here in quadrant 3 this time, which remember, quadrant 3 is negative, negative. All points here are negative, negative. And in quadrant 1, as we already said, all points are positive, positive. So, starting with quadrant 3, as x approaches negative infinity, so once again that's left, as we go left, f of x is going down towards negative infinity. Now look at quadrant 1, as x is approaching positive infinity. In other words, as we're going right, what's happening? It's going up. Where? Towards positive infinity. So here's quadrant 1, here's quadrant 3, here's quadrant 2, and here's quadrant 1. Alright, now each polynomial has key features that make it unique. We're looking for the zeros, which we also call x-intercepts. We also call roots. We're going to keep using these terms interchangeably. Okay, so we look for the x-intercepts. That's one thing we're looking for. Then we're looking for, secondly, the end behaviors. Then we're also looking for local maximums and local minimums. Sometimes they're called relative instead of local, depending on which book you use and who's talking about it. Okay, and these are the turning points of the polynomial. If you think about that when we talk about quadratics, we talk about the word maximum and minimum, and we use the word vertex, the vertices, okay? And remember the vertex was the highest or lowest point in a quadratic. Well now, as we're getting into more advanced stuff, we have these waves where it's going up, hitting the ceiling, going down, hitting the floor, going up like a ball bouncing. Well, if you look at this chart here, this picture, got a lot of stuff going on. X-intercepts, once again known as the roots, zero solutions, are located on the x-axis. We have 3 of them right there. Okay? Then, over here, we have a maximum. And if you think about looking at just the left side, it looks like a parabola, doesn't it? Okay? It actually looks like a positive and negative parabola that kind of merge together. So you have the highest point, and over here you have the lowest point in that section of the graph. Over here on the left, you have a little graphing calculator summation. And you're going to be getting a more detailed one, but this is a quick summary of how to use the graphing calculator. to do this, and we'll do more of this in class with a longer, more detailed handout. But the directions are right there. You can play around with it if you like. And once again, we're going to look at some other examples. Okay? Determine the number of real zeros and count the x-intercepts. So, as we just did in 3.8, we look at this and say, is it even or odd degree? Well, it's odd because it's 3. Local maximums, local minimums, we'll find that out. Number of real zeros, we'll find out, and our end behaviors. So if we graph this on a graphing calculator, which you should use, okay, put this in the graphing calculator, y equals x cubed plus 2x squared plus 1. And we graph it. And we're going to go to our table, okay? And we have some points off the chart. We have -3, -8, -2, 1, -1, 2, 0, 1, 1, 4, 2, 17 already going off the chart. So we can put some of these points on here to get a general idea of how it looks. -3, -8, -2, +1, -1, +2, 0, 1, 1, 4, and like I said, 217 is off the chart somewhere up here. So you can see kind of what this is doing. This is going up. Coming back down, and going up again. Now, like I said, we're going to do more of this in class to practice this, but if you go to these directions right here and try to find the maximum and minimum, so here's our maximum, there's our minimum right there, you'll find out that the maximum is at -1.33, 2.19, which looks about right. Okay, a little past -1, a little above +2, and the minimum is 0, 1. Now, the number of real zeros, there's 1, and it's going to be right there where it hits the x-axis. That looks to be about -2 point something. The end behaviors, well, as x is going left towards -infinity, y is going down towards -infinity. And as we're going right towards +infinity, it's going up towards +infinity. Okay, then for number 8, we enter in new one, -2 x to the 4th plus 4x squared plus 1. And we graph that. And pretty much off the chart pretty quickly. -2, -15, -1, 3, 0, 1, 1, 3, and 2, -15. So we put on what we can. -1, +3, 0, 1, 1, 3. The 2 is going to be down here around -15, right around there, and -2, negative 15, right around there. And now we get our shape that is kind of like an M. Which some of you saw those in 3.8. So, even or odd degree? Well, it is even, 4. Notice how they're going in the same direction. Local maximums, once again, there's 2 of them, 1, 2. And they're going to be at negative 1, 3, and 1, 3. They're right here. Those are our maximums. The minimum, right here, 0, 1. And the number of real zeros, right there and right there, 2 of them. Now let's look in quadrant 3. So as we're going left towards negative infinity, it's going down towards negative infinity. As we're going right towards positive infinity, we're going down towards negative infinity.